Okay, um, we are recording now, and let's get started. So welcome to the final lecture for this course. Um, the plan for today is there is no plan, okay? Which means we are going to, well, maybe a little bit. We were talking about assorted ideas and applications, various algorithms, techniques, methods that we've learned in the class. We were seeing how uh, research papers in this area actually take these different building blocks, these modules and algorithms, and they put them together in building various kinds of mobile wireless sensing systems. And let me refresh this website. 1 second. Yeah. And so we looked at, I think, 4 or 5 of them last class, and we might look at another 3 or 4, just to give you a flavor of the wide range of possibilities um, that you could potentially think about. After that, we'll just quickly talk about anything you want to talk about, maybe what kind of courses to take after this that builds on top of this. We could talk about industry, jobs. We could talk about your research opportunities down the line. Um, and finally, we might quickly look at everything we covered in this course. And if there are any questions you have on that, we can chat about that. And with that, I'll ask you to submit the feedback form for this class, and that is very valuable. I personally read all the feedback. So that's basically the agenda for the class today. Okay. Any questions thus far? Okay, as usual, thank you very much, Deep, Anthony, Alex, for consistently keeping your videos on. Shreyas, thanks for coming today. I don't know if you wanted to say something or any particular reason, but glad to see you.
No, I just thought I'll come in since my other class that conflicts with this was shorter this time.
Okay, good.
So I thought I'll attend the last class. And I also have a small little thing to share, not as important. We can share it at the end.
Sure, sure.
Mhm.
Okay, so let's quickly jump in. And I hope you were having a little bit more fun away from the math and stuff, because now we're really looking at, you have these Lego blocks, what stuff can you build with these Lego blocks, right? And we started to talk about insight. You remember where we said that the camera can look at the person moving around, understand the motion from the camera's pictures or the screen buffers, compute the motion and use that motion as an address to communicate to the person. And I think it was tickling to think that a surveillance camera in UIUC campus would tell the thief who's stealing a bicycle that I see you, and with a pop-up message on the thief's smartphone, right? So this kind of a communication to a complete stranger, which is privacy preserving yet very location specific, is something that Insight does. And again, all these papers are over here, so I would encourage you to kind of read the paper or even the introduction, quickly browse through the paper if that interests you. Okay. After Insight, we talked about Y-Track, where we looked at that video where wireless signals from a Wi-Fi-like device is sending out the signal. This is like radar, right? Radar was actually patented, I think, after the Titanic disaster. The Titanic ship did not realize that there was this big iceberg. And then they started thinking, how could we have known? Because what we see is not what we get, right? Under the water, the iceberg is huge. So that prompted these thoughts around, can we send a signal and look at the reflection of the signal? And from that, understand that there is an object in the trajectory. And from there, things revolutionize, right? Because now we use radar not only for planes and ships and submarines and torpedoes, but also for climate, because now we can understand where there are clouds and where there are hurricanes building up and tornadoes building up. And then now we use radar for self-driving cars. I mean, it's not called radar, it's in the optical domain, which is LiDAR, but the principles are still very much similar. You shine out laser lights. In fact, with LiDARs, you have this spinning laser, which kind of sends the laser in all different directions and looks at the reflection of that direction. And from that can image the environment around you. And then essentially what Weitrack and several other and other papers along this line is saying, can we bring these kind of radar techniques inside the home? Now one could say, oh, how is that? Why is that different? We already know how to do radar. But one of the important distinctions is inside the home, the multipath is tremendous. Right? There's too many signals that are reflecting, which is not the case for a submarine or for an iceberg or for a plane flying in the sky, or for weather, simply because there are line of sight paths dominate the reflections. In an indoor environment, in a small house, in a small apartment, that is a much bigger problem. And within that, the motion of the person is a much smaller kind of, if you move a little bit, the reflections are changing small. So it's a needle in a haystack problem where there are so many of these signals reflecting back to the wireless device, your Wi-Fi router, and your Wi-Fi router has to wade through all the details and kind of pick up the signal, right? Which exactly pertains to the reflection from your body. And if you're interested, there are subsequent work where they're saying, oh, can I even understand the gesture that you're doing? For example, you're drinking a cup of water or you fell down. And this is important in the applications of health monitoring, where a lot of senior citizens live independently, but the worry is if they fall down and they cannot call the ambulance or 911, what do? How can we automatically figure out that they've fallen down? And you don't want a camera in their houses to always track them. That's a privacy issue. So wireless signals is one way to understand that. And in that context, we saw how canceling out the signal is possible, where you send these signals in a particular pre-coding, and we saw how that is connected to adaptive filtering that we've seen in the context of noise cancellation. You have to estimate this H1 times H2 inverse. And from that, you can start subtracting out the background clutter and only understand what is reflecting from the user. Another radar style technique that we saw was in this context of CAT, where we want a remote and we want to move the remote, and the reflection from the remote in acoustics should tell you where the remote is. And that goes into what we call FMCW, a frequency modulated continuous wave. And we said that the idea is actually very simple. You change your frequency at a particular rate, right? But when the signal reflects, the signal that is reflecting is of a frequency that is different from the frequency that you are getting directly from the transmitter, right? Because you're constantly changing your frequency. And then we said, oh, how do you actually figure out the time it took for the signal to reflect? Because that's the time we care about. If you want to know the distance of an object, we shine a signal, the signal goes and reflects and comes back. What the distance of that object is proportional to how much time the signal took to go and come back, right? So that's really what we care about. And we said that, oh, look, we know the slope of the frequency of the FMCW signal. We know the slope. We know the difference between these two frequencies, because the signal that's coming back and the signal that's coming directly, we are multiplying them. And remember that we talked about in the context of backdoor, where the signals, the frequencies were getting multiplied. And once two frequencies or two sinusoids multiply, the resulting sinusoid is F1 plus F2, F1 minus F2. And that is how FMCW works. And once you know F1 minus F2, which is this part, and you know the slope, then you can say tan theta is F10 minus F5, which is F10 minus F5. That's tan theta, and that gives you tau, and half of tau is the distance of the object, right? Half of tau multiplied by the speed of sound is the distance of the object. So FMCW is actually used in self-driving cars as well, where they use wireless signals to understand the environment. And why would they use wireless signals instead of LiDAR? And one of the reasons is in fog and mist and rain, LiDAR doesn't work very well because things are occluded. Rain and fog occludes these lasers and they also diffract a lot. But if you use wireless signals, those wireless signals penetrate fog much, much better. So in these kind of adversarial climate weather conditions, you might want the radar to have a wireless frequency as well. And that's where FMCW becomes interesting.
Wait, sorry for asking this question.
Yes,
Why were the sine waves being multiplied again?
Oh, if you remember in backdoor, so in FMCW, the signals that come back and the signals that reflect and come back to your microphone, there's a way to multiply these signals. So the FMCW radar circuit actually multiplies the signals that arrive at the receiver. Okay. And one example of multiplication of signals that we had seen was in the context of backdoor, where the multiplication was essentially a squaring. Remember, we said that in backdoor, the nonlinearity causes this this component A2 times V in square, where V in is the incoming voltage on that amplifier, right? So V in square, if you have a sine F1 plus sine F2, and that squared would be, there would be, if you work out this whole equation, sine F1 plus sine F2 whole squared, you will see there is an equation, there's a frequency component sine F1 plus F2 and sine F1 minus F2. And in backdoor, you remember sine F1 minus F2, sine F1 minus F2 was what was becoming audible because we had squared this V in. And even in a FMCW radar, when the signals come in, you actually multiply the incoming signals. And as a result of that multiplication, you have a component which is basically F10 minus F5. One way to think of multiplication is squaring. Right? Whatever signals coming in, you square. Right? And you will see a component which is this F10 minus F5. And once you know F10 minus F5, you know one side of the triangle, you know the other side, you know the slope of the triangle, therefore you can compute tau. Utkarsh, does that make sense?
Yes, thank you.
Great. And then we switched gears completely and we talked about this other application in which we were sending this wireless signal through a liquid. And because of the refractive index of any object or of any material causes signals to bend in that material. So in school, when we learned about refractive index, we learned it as, oh, the signal arrives at an incident angle theta and bends with an outgoing angle of alpha. But another way of looking at refractive index is actually looking at the velocity of the signal. The velocity of the signal changes as a function of the refractive index of the signal. And that change causes the wavelength to change. And as a result of that, because the frequency cannot change, the wavelength changes. And as a result of that, the phase of the outgoing signal changes. And from that phase, you can start inferring how much is the slowdown of the signal. And if you know how much the signal slowed down while it was going through the liquid, that tells you what the refractive index is. And from that, you can start inferring other properties of the liquid, such as permittivity. Okay. And once you know permittivity of a liquid, that is kind of a, I would say, it starts to become kind of a signature of the liquid. So much so that you can start separating Coke from Pepsi, from vodka, from mineral water, from cooking oil, from all kinds of other liquids. And if you want, I can show you a quick picture of the various liquids that is possible to separate. So this paper separates all these liquids, starting with distilled water, mineral water, orange juice, apple juice, grape juice, Pepsi, Coke, Diet Coke, salt water, glucose, milk, whole milk, etc. And this is what the confusion matrix looks like. You see, it's largely diagonal, meaning most of it you get right. Of course, there are places where you don't get it right. These places, of course, you don't get it right, but you have reasonable good signature from the permittivity of the liquid itself.
Are the permittivity values for these liquids known beforehand?
Yeah. So in this paper, what we did was there's a physics manual, there's a physics handbook in which they tell you the permittivity of different liquids. You can get those data sheets. And we also had this, we also took each of these liquids and put a probe in that liquid from a network analyzer. And that network analyzer was able to measure permittivity, but using all these highly expensive, complicated equipment. And by dipping a probe in that liquid, you can measure permittivity, right? You sense electricity through the signal and get the electricity back passing through the signal. From that, you can do the inference, but you need to get the liquid out. So this was kind of a way to understand what was ground truth. And here is the table that tells you what the permittivities are for different liquids, and the baseline means what we pulled out from those network analyzers, those oscilloscope kind of kind of devices. And liquid, which is this cheap wireless technique, that's the estimated permittivity, and they match reasonably well. While we were doing this project, this was perhaps one of the most popular projects in our building because we were buying vodka and wine and beer for the purposes of research. And that made many students want to join our research for only that project and not for other stuff. So it was a fun project, and there's a lot more interest in this project because now people are saying, what can you say about blood? Okay. What can you say about mixtures of liquids? So the idea is, can you basically take your mobile phone, shine a signal onto your hand, and understand properties of the blood, so on and so forth. So spectroscopy. Spectroscopy is typically done with optics, very wide bandwidth. This is poor man's spectroscopy, but could have interesting applications. Okay. Great. And then we started talking about a related project where we said, look, digital agriculture is becoming very popular, where you essentially want to understand exactly what a farm is doing, where is the moisture, where is the fertilizer, what kind of chemicals are there in the farm. And there's this project that's called Strobe, which talks about low-cost soil sensing using Wi-Fi. And the idea they have is really here, where they want to send signals from a wireless Wi-Fi transmitter, perhaps from a drone, and the signals should bend in the soil depending on the moisture content of the soil, right? Similar to how liquid is. And I think they build on top of liquid to some extent. And now if you have an array of antennas, I don't know how I can annotate this. I don't think I can. Yeah, I don't think I can. But okay, I'll use my cursor. If there's an array of, this is an array of antenna actually, okay? This is a receiver. And this is exactly doing d cos theta, right? And they're figuring out what the phase is, the relative phase is. And they know what the distance is from the surface of the soil to each of these antennas, because they know how deep they have put the antenna underneath the soil. So now, because they know that, they can estimate d cos theta and thereby the delta phi. And from the delta phi, they can say how much the signal refracted inside the soil. Okay? And if they know how much the signal is refracted, they can connect that to the moisture content of the soil. And as a result of that, here is where I think they already have Wi-Fi transmitter underneath the soil, and therefore using the same Wi-Fi receivers, and using the same Wi-Fi receivers, applying beamforming algorithm, but with these refractive indices kind of ideas, you can now start estimating what is the moisture content in the soil. Okay? So these signals are coming in and they're bending. And those thetas is what you really use. Those delta phi's that you estimate over here is what you really use to estimate moisture. Okay. So this was actually a very exciting piece of work, simply because many farmlands are already inserting wireless devices underneath, sensors underneath the soil, and also wireless signals penetrate a lot deep into the soil. So if you want to understand what is happening underneath, where the root systems are, it's actually possible to put in these wireless systems, as opposed to digging up and putting a sensor and then communicating to the sensors is difficult, and battery changes and all of that. But these wireless devices, they have power cables running, so they have connected to these wireless devices anyway. Great. Okay, now let's look at a very different idea. We are switching now. This idea is called spiky. Okay, and here is the idea. Let's look at the paper. The title of the paper is Listen to Your Key Towards Acoustic-Based Physical Key Inference. And the idea is, when you insert a key, a physical key, in a lock, and you turn it, the sound that the whole operation produces can reveal the shape of the key. Okay? Again, imagine an attacker standing near the door when you're opening the key with his smartphone microphone on, recording sound. Now you are inserting your key in your home entrance's lock. And as the key inserts into the lock, the bitings of the key, the ridges and the bitings of the key make a sound based on where the touch points are. Right? Eventually the bitings go and I kind of hand in glove with the lock's ridges, right? And then you can turn the key. But while the key is moving in, it's touching the different ridges of the lock, and that creates a sound. Okay. And what they show is that if you record that sound with a microphone and you pull out the phase differences, because each of the sounds are produced from a different location. So the sounds are coming from the sounds come with different phases. Okay. So if you can look at, and then finally that click happens. So if you can actually pull out the phases of each of the sound components that are coming from each of the bitings of the lock and key, you should be able to understand exactly what the shape of the key is, and thereby that's a major attack. So this actually, maybe this is an interesting paper to read. This requires you to know FFTs, beamforming, delay sum, phase differences, triangulation. Okay, those are the building blocks on which this kind of an attack is built. And they said that the results say that from a given recorded sound, they can come up with 3 possible candidate key shapes. Okay, it's not an overdetermined system, it's an underdetermined system, meaning that you do not have enough information to precisely image, to precisely understand the key shape. But even though it's underdetermined, you can prune out possibilities and come up with 3 candidate shapes. So as an attacker, you want to attack that house, you basically create 3 keys and you come and you try each of these 3 keys, one of them will open.
I have a question.
Yes.
Does this paper go through a solution to this problem, or?
I don't think so. Wait, let me see.
I don't know, like, is it like ethical to, like, you know, detail this without?
Yeah, I mean, security community is known for coming up with all kinds of attacks because it's good to come up with attacks because that way you know what to defend against. Right? A lot of security research is around coming up with absolutely crazy radical attacks, because if you don't come up with the attacks, someone else will and you won't know. So the research community wants to come up with as many attacks, even though you don't have solutions to it.
It just seems like even if you do come up with a good solution to it, like how quickly will it be adopted before, you know, people?
That's true, but it discourages the attacker in some sense, because they think, oh, the risk of me trying to do this attack and then getting caught, right, is now higher because these solutions are rolling out. So maybe I should not try to attack in that way because maybe I'll get caught. Maybe people have already installed these kind of things.
Okay.
Yeah. But a lot of research happens without having a straight path to adoption. People just do the research anyway. And there are other people in the government and other agencies who are saying, oh, that's an important one. Let's push for the solutions for these, right? I mean, for example, Android and iOS and all these kind of operating system bugs are coming up all the time. And a lot of researchers are showing that, oh, there are bugs, and these companies are very diligent about taking these bugs and trying to plug those problems. Yeah. So this paper, I don't think they give a solution, but hey, maybe that's something, if you're interested in, think of how you can actually solve the problem. Great. So this is something I thought was interesting in a way that it actually creates an attack, but the building blocks for this attack depends on everything that you know from this course. Okay, next one. Again, we are doing a rapid fire. This is another interesting one. So this paper, this idea says, we are going to do software-defined cooking using a microwave oven. Okay, so what is the idea? You know how microwave ovens roughly work, right? They basically send out electromagnetic signals, and they create a standing wave inside that box, right? So they make the lambda of the signal a multiple of, they make the size of the box a multiple of the lambda. As a result, the signal in the box looks like that. Okay, and these are the regions where there is good amount of energy. Of course, they change the frequencies, and so these are called nulls. Hey, that's beamforming, right? This is the same kind of null, right? And these are called the anti-nulls. And the turntable turns so that different parts of the food come to the anti-null positions or the main lobe positions at different times. Otherwise, if the turntable did not turn, then the food over here will get heated much more and the food over here will get heated much less. Okay. So this paper says that, look, this is not good enough, because even though things turn, I might want certain parts of the food. If it's a rice and if it's chipotle, I might want the rice to not get heated too much and I want the vegetables to heat. Or I want the bacon to get much more heated and I want the rice to be less heated and I want the vegetables to be a little bit heated, or different combinations. So why don't I program the way heating is done in 3D space inside the microwave? Okay. And why shouldn't I be able to program? Because this input signal that I'm giving to the microwave is in my control, right? And not only that, on top of that, they say, if there are some if there are some things that you don't want to get heated, you can even put objects on your plate. So one thing I learned from this paper is that if you put metal inside a microwave, it's not necessary that it'll create sparks and it'll explode. It is only sharp edges of the metal that creates these kind of sparks. If you put a metal ball, a metal sphere inside the microwave, nothing happens. Okay. And then they said that, oh, here is, if you have a few of these metallic objects and you control the input signal, and you have some way to understand which parts of the microwave is heating up to what extent, you can completely make it a programmable microwave where everything can be controlled based on some objective function of how much you want to heat the rice, how much you want to heat the chicken, how much you want to heat the vegetables. Okay. So here is an example of where they actually put they wanted to program the microwave's heating, so they put different objects in the microwave, and they're saying here is no turntable, which means the heating in the microwave is very uneven. This is the default turntable, which is a little bit better than no turntable because at least because of rotating, the heat dissipates a little bit more. Right? This is uniform heating where they can control the signals inside the microwave so that the microwave heats uniformly across the board. But then you may not want, if you put rice inside a microwave, you might want unified heating, but you may have different things on your plate and you may not want unified heating. So they also say here is precise heating to the extent that I can write out any word that I want. And they wrote out the name of the conference by precisely controlling how they want to heat. Okay. And the building blocks, so what they really do is, actually I can show you the pictures over here. Okay, so first what they do is they control the input signal to the microwave, that they can control the frequencies, and as a result they can control the wavelengths, and as a result they can control the places where the microwave is getting heated. That's number one. Number two, they put these neon lights inside the microwave, right? You somehow want to know which parts are getting heated, which parts are not getting heated. So they put these neon lights inside the microwave, and these neon lights actually scavenge energy. Whenever there's electromagnetic field, they get energy from that field and they light up. Okay. And they don't need a battery. You cannot put any sensor inside the microwave which has a battery. That is dangerous, right? So they put these lights inside the microwave, and the lights use the ambient energy to light up. And as you can see, these lights are lighting up. Okay. And then they put an external camera which looks at these lights lighting up. And from that, they can understand what the energy distribution is inside the microwave. Right? Third, they say, look, if I want to cover the chicken and not give too much of radiation, but not cover the rice, I can also use these microwave shields to actually guide the RF energy inside the microwave. Okay. So this is another degree of freedom that you have in order to basically guide the signal inside that 3D box. And finally, this is kind of one example where they put two kinds of rice on the same plate on two sides, and they're able to heat them in a very different manner. Even the same thing in a very different manner. Okay. Of course, you have to solve some optimization problems. Clearly, you see why this is an optimization problem, right? You have a 3D box. You have certain places you want energy. You have certain places you don't want energy. And the degrees of freedom you have is the turntable, the frequency of the signal, and the measurements you have is from these lights that are glowing based on where the signals are high and where the signals One important point is if you can control exactly where the signals are, why do you want to have these lights? You exactly know where the signals are. You can model, right? Right? If you know exactly where the signals are, and if you change the frequency, maybe the frequency is like this. Sorry, okay, I didn't draw that correct. But if you know exactly where the signals are, then you should not have to worry about lights. Oh, but can someone tell me why you still need to know where the signals are and why do you need the lights? Why is it not good enough to say there is a null here, there's a null here, there's high energy here, there's high energy here, there's medium energy here, there's medium energy here? That should tell you everything about what the energy looks like inside this microwave. Why do you need the lights? Ideas? Okay. The reason you need the lights is that the stuff on your plate is unknown. Right? So whatever plate you put over here, let's say there's a bowl and there is rice and there is chicken and there are vegetables sticking out and blah, blah, blah. That is going to change the energy distribution inside the microwave. Right? And that's why you need to know the lights is essentially a measurement of how the energy has changed. And by looking at the lights, you can start to model, I put in energy that has this spatial distribution, but some pollution came in because of the plate. And as a result of that pollution, I see these lights that are glowing, which tells me how my expectation and how reality is disagreeing. And from that, I can do my optimization. Okay. And they show that they can, I mean, here is something else where they put in these accessories along with their rice to really have more control on which parts of the rice they want to heat and which they don't. And here is an example of bacon, which is one is raw, one is default rotation. And in the default rotation, I think some parts heat up much more and some parts heat up much less. But with software-defined cooking, you've cooked your bacon perfectly. Okay, I thought I wanted to give you a sense of how far you can go, right? Building crazy but exciting creative things with these building blocks. Okay, next. Here is a paper. So let me see if it loads. Okay. Here is a paper that says the following. They say, you know, drones, when drones fly and they change their directions and they move up and they move down, they have to use IMUs. Why? Why do they need IMUs? I think we talked about this once. When they take a turn, the rotors spin at different velocities, at different angular velocities, right? Now, the controller in the drone has to figure out how to change these rotations based on how much the drone is turning, right? If the drone has turned a lot, the rotations have to change to stabilize them once again. But how does the controller of the drone know how much it has turned? For that, it uses the gyroscope, right? Because it wants to understand the rotation of the drone, the pitch, yaw, and roll. Now, if the gyroscope gets affected, then the drone will get basically destabilized. And I don't know if you remember the Boeing 737 Max's all kinds of accidents. Part of it came from the gyroscope because the angle of attack when they were taking off, the gyroscope was giving erroneous readings. So the plane thought that it is like in a small angle when it was already like that. So the pilot would think that, or the plane's auto takeoff would think that, oh, the plane should actually, the nose should go higher. Actually, the plane is already pretty high, but the gyroscope is saying the plane is low. So the plane would even go higher, and that would make the plane crash, or even while landing. So gyroscopes are integral to all kinds of drones and planes and flight control, flight stabilization. This paper shows that if you send a sound signal towards a gyroscope, and gyroscopes are, by the way, MEMS devices. What are MEMS devices? At a very high level, there are micro electromechanical devices, meaning some things vibrate inside, some things move inside. Okay. In fact, one high-level way to think about accelerometers, for example, let's call this gyro attack. One high-level way to think about accelerometers is the following. It's like, again, I do not know this very well, but from what I have read from high-level articles is that they have these metal comb-like structures. These are the combs. And these are also the combs. And these are MEMS devices. Okay. And when they move, these combs, they move like that. They physically move like that. And because of those physical motion, the capacitances change between these two. And that capacitance change is what tells you the force that the MEMS device is experiencing, and they translate that force into acceleration. Okay. So these are called MEMS devices, where something is moving that is creating, transducing into some electrical effect, and that electrical effect gives you the output voltage, which gives you the measurement. Right? So MEMS devices, micro electromechanical systems. So gyroscopes also operate on a similar kind of a technique, except that it's not moving linearly, it's doing some rotations. Now, if things are moving, you can make it move through external force, but more interestingly, if you give a signal to this object, which is at the resonance frequency of that object, then that object will start moving crazily, because that becomes nonlinear. All kinds of destabilization happens. So this paper says that, look, you can send an ultrasound signal, or even a high frequency, almost inaudible signal, design the signal at the right resonance frequency of the gyroscopes, and you can completely crash a drone. So there have been designs of ultrasound guns that point towards a drone. Of course, ultrasound signals absorb a lot, so you have to generate a lot of power to point towards this drone and send it far away. But if the drone is not too far away, and if you can generate power, and if you got your frequency right, and maybe you can even search in the frequency space to kind of find which one is resonant with the drone's gyroscope. But you can create this gun that will crash any drone that's flying because the gyroscope is affected. Okay. And this paper shows that such resonant frequency-based attacks are very much possible. Okay. In fact, that reminds me, there was also an attack on Amazon Alexa, which was of the following. The sketch of the attack is the following. If you shine a laser light on a diaphragm, by controlling the frequency of the laser, you can make the diaphragm move a little bit. Okay. So what one can do is from far away, you can shine that light on the diaphragm of the microphone. And by controlling the frequency, you can give any voice commands to Alexa. Right? So imagine you stand at your window and your neighbor has an Alexa that is visible to you. It's in line of sight, even if it is behind a glass window. You can shine a laser light towards that Alexa, and if you modulate the frequencies right correctly and the diaphragm moves accordingly, you can even inject a voice command and Alexa would do something for you. Okay. Crazy stuff. Great. Okay. So that is gyroscope attack. Okay, I don't know why there are so many of these security papers, but maybe security papers are a little bit more fun to read because, oh, these are things I can do with these Lego blocks. I mean, that's the kind of feeling. Okay, maybe another one. Let me see if I have a video of this. Yeah, I think I do, yeah. Can you hear? Yeah. Okay, so the idea is you're wearing a smartwatch and you're typing on your keyboard. Okay. Your IMU is recording your hand motion, your wrist motion. Can you figure out from the IMU what you're typing? Okay, that's the question. And it turns out you can. Let me say that if you just look at your IMU data, you will know how the wrist moves, but that doesn't tell you what fingers you are typing, right? So suppose you get recruited by a attacking agency with a lot of salary, and therefore you've taken the job, even though you're going to do bad things, or maybe doing bad things is exciting, I don't know. You've taken up the job and the attacker CEO says, hey, you've taken 434. Here is an attack I want you to launch, which is from the IMU data, I want you to figure out what these users are typing, and we'll use this to surveil high-level officials and do spying and all kinds of stuff. So think about this problem. You have this IMU from your wristwatch and you know how the hand is moving, and let's say you know very well, you can do dead reckoning very well that you know how the wrist is moving. How do you translate that to keys that are getting typed on the keyboard? Any thoughts? Okay, let me say.
Oh, sorry.
Yeah, Adil, go ahead.
It seems kind of hard because like you can have different typing like methods, right? Like say some people use their pinky for the A key, right? And some people use their ring finger for the A key. Those
Correct.
are two distinct wrist motions, right? So
Correct.
maybe you'd map those wrist motions to the A key, maybe? I'm not sure.
Okay,
Like,
so one way to do it is if you can somehow figure out, if you have some training data from the user, right? For example, I ask you to wear this watch and type the fox jumped over the wall. I think there's some sentence which has all the alphabets, all the characters of the alphabet, right? So the fox jumped over the wall or something. So you type that word or that sentence, and from that I know how much you moved, and from that I can calibrate that, right? That's one way of doing it. But that requires training data, which means as an attacker, you have to go to this high-ranking official and say, hey, can you please wear my watch so that I can attack you, right? I mean, no one's going to give you training data for that. What else can you do?
Use an HMM maybe?
Ah, that was the word I was looking for. Okay. Here is an application where you can again use HMM, right? In other words, you say, look, I do not know what my fingers are pushing, which key my fingers are pushing, okay? But given the wrist location, maybe I have a bunch of candidates that my finger can push, right? I mean, given this left wrist location, you know that it cannot push Y. You know that it cannot push U. Agreed? But you know that it's likely pushing C, D, S, A, or maybe even what is besides C, V. But you don't know out of these 5 which candidate it is. But this is where immediately you should think hidden Markov models, because this guy is typing. It's not that he's going to type random characters, right? If it's typing English language, then you know there is a state transition diagram that you have, and you have some measurement, your IMU measurement, which does not give you the exact location of the finger press, but it gives you a distribution around that, which was your P M given S, that distribution you have, right? Hidden Markov model. But now you know you can do even better. When you type with your finger, do you think your wrist stays static? When you type with your finger, your wrist also actually dips. Right? Now, these are all bonuses. Your wrist would dip. That would tell you the strokes of the timing of the keys. Right? So you know that. But there are still challenges. Your right hand doesn't wear a watch. So you're only using your left hand. Right? But if you know when the dip is happening of your wrist, because that's the timing of the keys, then you can also start to estimate, I pressed some alphabets, then I pressed on my right hand, and then I pressed on my left hand again. So you also know the difference in timing. I pressed a character, I did not press maybe for 2-3 characters, and then I pressed this character. So you can play now Hangman. I don't know if you know this game Hangman, right? But I tell you a bunch of dashes for a word, and I give you a few of the characters in those dashes, and you have to guess the rest of the dashes, right? You can pull all of this together and you can start predicting what the user is typing. Okay? I'll play this video so you kind of see what is going on roughly. What do you think this system cannot guess what the user is typing? When can the system not guess what the user is typing?
If there's like words that are only typed with the right hand.
Say that again.
If there are like English words that are only typed with the right hand.
Only typed with the right hand, you cannot guess. True. Right? But as an attack, you have to tell your CEO, boss, I will get all the English words that are getting typed, but I cannot get you passwords. Right? Because passwords don't have the same HMM, is not going to follow the HMM state transition probability matrix that you're going to use. Right? So passwords are difficult to pull out.
So probably numbers?
Probably numbers too, exactly, right? Because numbers don't have any of that state transition matrix as well, totally. Right? But if you use passwords which have English words in them, now you know why there is so much of hue and cry about, please don't use English substrings. Right? So need to be careful. Okay, video. Oops, I don't know why it's going to the beginning. So this part shows how the system is figuring out where the key presses are happening, okay, on the keyboard. Okay. Oh, actually, sorry. This part is from a ground truth camera that is placed on top of the wrist that is actually tracking this green sticker on the watch. Okay, so this is ground truth where you exactly know from the camera which key the user is pressing. Okay. Can you say what word the user is typing from this? Confident. Okay. O is on your right hand, N is on your right hand, but the others are on your left hand. Okay. That confident is the word. Okay. So this is IMU, actual IMU data. So this is actual IMU data where you see the dip happening for that key press. And that's when you map the IMU data to the keyboard's layout. Okay, so now comes to the question that Adil was raising. How do you know? Some people might use the pinky to type the A, some people might use the next ring finger, right? You don't know, right? So, but what can you do there? Can you, now your CEO boss is saying, Mr. 434 student, people are going to type differently. So what can you do? Okay, so this is what you can do. Even though people type differently, if you look at the distribution of how their hand moved, you should be able to map it to the keyboard, right? Right? So if I type the faraway letters with faraway characters with my pinky, my hand motion is going to be more restricted. But if you assume that I'm typing all the keys, you can take my hand motion and scale it up, right? To understand how it actually matches the whole keyboard, right? So this is what this paper also does. The attacker types himself and gets what his distribution of his arm looks, of his wrist looks like. And then he gets the attackees, the person's motion patterns. And he says, first he says that, look, the motion pattern of this attackee, let's say that's some terrorist, right? You're working in as a CIA agent. This terrorist hand motion, you say that, look, in distribution, it should match my hand distribution. Okay. So you basically scale it. I'm pausing it and it's taking a while to pause because I think it's going over the internet. Anyway, so now you apply maximum likelihood, right? You have an idea that when the wrist is over here, that user is pressing one of these keys, right? And now you know that the red dot is where the user pressed the key. So now you apply maximum likelihood and you say, from previous models, I see that red dot can be R with this probability, can be T with this probability, and so on. And then you, on top of that, you apply the probability transition matrix. You say, oh, given the previous character is M, could this be a T? Oh, that probability is very low because T followed by M is all very, very rare, right? So you apply that on top of this. Okay, so this is the result. This says that if you type a word that is longer than 6 characters, Mole will, okay, by the way, the name of the project is Mole, motion leakage, but Mole is like, your spy. Mole will shortlist 10 words on average that will include W. It cannot tell you the exact word, but it includes W. But it will give you 10 candidate words that will include W. And now if you write a sentence, of course, you can start pruning, right? And maybe here's a puzzle for you. Wait.
While you're pulling that up, can I ask a question?
Sure.
So you said like in order to decipher between the different methodologies of typing, the attacker can use a certain technique. Is that technique like constructing the probability matrix? I forgot what it was called. The observation probability matrix, or?
No, but here is the technique, Adil. So this is exactly the question that you're asking. The light gray points are actually, let's say, the attacker's wrist motion and the key taps.
Yeah.
As measured by the attacker himself.
Yeah.
And the black points are, let's say, what you get from the person that you want to attack. Right? These are all the keystrokes that person made. Right?
Yeah.
But given that the person, you're assuming that if you have enough data from the person has typed all over the keyboard, which means the black shape, the black convex hull should match your convex hull. Okay, so the black shape should be expanded and rotated to match your shape, because the person might have long fingers and therefore the person needs to move a little bit to type. You might have shorter fingers and therefore your wrist moved a lot more. Right? This is what the gray and black shows. So if the person had long fingers, all you need to now do is you take the person's data and you scale it up, rotate to best match your data. And now once you've scaled up and rotated, now every key press, you should be able to figure out where that key press is likely coming from. So this is a model fitting question. I don't know if that makes sense, Adil.
What is CPC here?
Say that again.
What is CPC here? CPC and UPC in the graphs?
Wait, I've forgotten.
Unlabeled and
yeah, I think it's
I can go back into the paper and see it.
Sure. Yeah, if you just look up, just Google, just search in that paper and you should see CPC and UPC. Oh, here. Character point cloud is CPC and UPC is unlabeled character point cloud.
Okay.
Yeah, if you're interested, read. Okay, but here is the what time is it? Okay, 11:06. Where is the, oh, here. Okay, here is one of the results from Mole. The user typed a sentence. The first word of the sentence, Mole gave this as the output. So the word could be motor, monitor, them, the, then. Motor is not sure. Sorry, Mole is not sure. And it gave 5 candidates for the first word. It gave 5 candidates for the second word. It gave 5 candidates for the third word. Question is, can you say what the terrorist was typing? Let me help you out. I think if you stare at it for 5 minutes, you'll figure it out. Again, because of the English structure. But let me say the first word is the.
Based on grammar, probably most.
Okay.
And
good.
then
Already got that. The most.
third would probably be an adverb, so like originally or original, one of those, or profound, either of those.
Okay, so it cannot be originally, right? Can it be originally?
Yeah, you're right, because there's no adjective in W4.
Right. So the most, it's either original or profound. Most likely, no? I mean, of course, you might be able, the most profile, I don't know if there's some way to even include profile, but okay, let's even include that. The most profound, original profile, right? If you were to put a bet, I think you'll put your bet on original or profound, right? Okay, let's go with that tree. The most original or profound, and then what?
It's W5 that's like really confusing. Like W5 doesn't really.
Remember, W5 might be, the actual word may not be in the short list.
Yeah.
Okay, let me tell you that W5 is not in the short list. Okay, I mean, again, in the interest of time, I'll move forward. Okay, if I tell you the W4 is technology.
Yeah, I don't know.
No, I know it's hard. I know it's hard. Okay, it says the most profound technology. R is missing, A-R-E, are those that disappear. In fact, actually what we did not do thus far, when we were trying to decode, we did not take the rank into account. We should have taken the rank into account, right? Because if Moll is saying that, look, profound and technology and those that disappear, right? If Moll is saying those are, I'm more confident about those, we should have given more weight to those, right? So when deciding between profound and original, we should have gone for profound, right? Or we should have put more belief in profound, right? In fact, you can even run a hidden Markov model on top of this, right? To say which paths are more likely, applying Adil's idea that, oh, it has to be adverb, it has to be followed by a preposition, blah, blah, blah. If you apply those constructs, you might be able to bring it down to 4 sentences, right? So there's more room to play with, right? Using the English language's structure. Great. Okay, and the last thing I want to say is, I think I've not talked about hearable computing, which is something that I think is an interesting area that is beginning to emerge. And the idea is that tomorrow or in the next 7 years, earphones might actually be the next smartphone. Okay? And there are a lot of thoughts going into this. And here is a paper that I kind of recently wrote up with all the thoughts on how earphones could actually change the landscape of mobile computing. And I encourage you to look at the paper. But one of the problems I want to quickly tell you from hearables is the following, which is relevant to 434, is the following. Okay. When human beings hear sound, they can figure out the direction of the sound. How? Maybe we talked about this before.
They use their time difference between the ears to localize.
They use the time difference of arrival between their ears. Okay. But this is like beamforming, right? This is like angle of arrival, time difference of arrival, right? The brain is computing delta phi, right? D cos theta. But in 3D, there are lots of points from which the time difference of arrival is the same. There are lots of angles from which the time difference of arrival is the same. So then how does the brain figure out?
I think it has something to do with the shape of the year.
Correct. It turns out when the signals come and impinge on your face, the signals bend on the surface of your face depending on the structure of your cheekbones, the structure of your nose, glasses, etc. Moreover, the signals encounter micro echoes on this part of your ear, which is called the pinna. The grooves in your pinna are very carefully designed by evolution so that it creates enough of echoes such that it helps your brain in figuring out directions of sounds. So the diffraction, you all know what diffraction is, right? Diffraction is when a signal bends. Typically, we think of signals going straight, but diffraction is when a signal bends around a corner. Okay? That happens too. So what the eardrum receives is a combination of your 2 ears distance combined with the pinna's micro echoes combined with the diffraction on the face, and that is enough to disambiguate which angle, which direction the signal is coming from. Okay. Now the distortions that your head has given to the signal can be thought of as a filter. Because that's a vector, and you take that vector and you convolve with the incoming signal, whatever the outcoming signal is, that is what your brain, your eardrum is receiving. So you can treat that as your incoming signal xt convolved with ht, which ht is your ear or your head. Gives you yt, where yt is what you receive at your eardrum. The FFT of this, now of course you remember, right? XF times HF will be YF because convolution in time is multiplication in frequency. This is called the head-related transfer function. And the question is, how do you measure a person's head-related transfer function? That's a research topic, and I invite you to look at that topic. It's very interesting to understand how the signal actually travels around your head. But the interesting point is, if you can figure that out, what can you do? Well, actually, you can do very interesting things. And one example of that is, let's say this is a person and now if you know the HRTF, okay, and now let's say XT is a sound which says, follow me. That's basically a sound signal. Follow me. You can take this sound signal and you can convolve with HT for the left ear and the HT for the right ear. You can convolve with both. Okay. And now through the earphones, you play, let's call this YYL and let's call this YR. So you play YL over here and you play YR over here. What do you think the human is going to think? If this HRT, if this HT is for some angle theta, the human brain is going to listen to that signal and think that the signal is coming from an angle theta in the ambience. So the human is going to hear a follow me signal coming from some angle theta, a follow me voice coming from some angle theta. So now imagine a blind person in a crowded, congested railway station or an airport wants to go to his or her gate, or why even a blind person? Even I get confused sometimes in a new airport or in a new train station, and I need to really catch the train, catch the plane quickly. Instead of pulling up my phone and really figuring out which way should I go, blah, blah, blah. Imagine this voice tells me, just follow me. And the voice comes from that direction and I just follow the voice. And the voice now says, follow me here, follow me there, and I keep following the voice, and I completely solve navigation in a much more nicer way. Okay. So, and it has many other applications. Imagine we all sit at a virtual table for a meeting. Now when on Zoom, we just hear each other flat. But if you could now think of VR, where we are sitting in a virtual table, maybe your voice, the person who's sitting on my right, can come from that angle. Someone else's voice who's sitting on my left can come from that angle. And I can play those sounds based on the configuration in which we have decided to sit in the VR world. Right? So this HRTF, and particularly personalized HRTF, is a very interesting research problem. And if you're interested, look at that. And of course, if you feel interested, look at this paper. And of course, there are a bunch of references along inside it. Look at this, because there are all kinds of interesting research topics, and even in industry. Facebook is very much into this. Dolby, Bose, Amazon, they're very much into these, because even with glasses that are coming out, you can start doing these kind of things. Okay, that's where we will stop. And just a quick recap of what we did in this course. We started with foundations in algorithms and techniques, linear algebra, signal processing. We started with linear algebra and signal processing. Again, foundations, there are much more to be done there. Please look at these books over here. They're actually nice hand holders. Then we went into localization, GPS. We talked about trilateration with GPS. We went into Wi-Fi localization, where we said, oh, one idea is fingerprinting. And then we said, maybe a better idea is channel fingerprinting, where we look at the multipath signals. Then we looked at beamforming and triangulation. We did AOA estimation using angle of arrival, using delay sum. And we also looked at subspace methods. One of them is music, where we said we can break the space, the whole column space of the matrix, into a signal space and a noise space. Then we moved into motion tracking. Motion tracking, we looked at IMU. We looked at IMU, various foundations of IMU, and motion tracking for human movement. We did some probability review, Bayes rule, conditional probability, and that led us into hidden Markov models, because we said, look, with IMU, there's no way of solving motion tracking, because IMUs will drift for sure. And remember, the problem was, if you're blindfolded and I ask you to walk straight, you'll never be able to walk straight, impossible, right? So you need some calibrations. And we said models of the motion, right, is where the calibration will come from. And we looked at hidden Markov models and basics into particle filters and other ways of correcting the errors. SLAM, we looked at SLAM at a high level. How do you correct with SLAM? Then we moved into a little bit of convex optimization. We talked about gradient, Hessian, convexity, convex functions. How do you test it's a convex function? But the reason we looked at convex functions is because we said that a local minima in a convex function is a global minima. And then we said, once we know gradient descent, we talked about gradient descent. Then we said that applies nicely into noise cancellation, into adaptive filtering kind of techniques. And we looked at noise cancellation. And then we said, oh, if you actually combine sound and wireless in noise cancellation, that opens up all kinds of interesting IoT architectures. We talked about vibration and acoustics. We said how we can encode data bits in vibration. And then we also talked about how signals can be, we talked about inaudible acoustics, how Alexa can be attacked by designing the signal carefully so that it goes through the nonlinear part of a microphone and makes the signal audible. Then we talked about dynamic time warping, where we talked about matching signals, and you've done MPs, you've done 6 MPs for all of these. And then finally, last class and this class, we talked about various ideas, assorted ideas and applications of how you can take these different building blocks and put them together. And to me, it's surprising how a few building blocks, few techniques and ideas and algorithms can open up so many possibilities. Okay. Moving on from here, I think there are a bunch of other courses that you could take. There's a wireless communication networking course that sometimes I teach, sometimes Haitham Hassani, Professor Hassani teaches. That would give you more in-depth understanding into wireless side of things, communications, wireless, beamforming, sensing. There's a wired networking side of things. I teach ECE CS 438, which is communication networks. I'm teaching that next semester. If you're interested in networking, particularly the internet and how things are evolving in the internet, that's a course that's good to have because many of these companies and systems and experimental research would need you to know about networks. There are topics in advanced networking courses and advanced sensing courses, 500 level at the grad level that you can take. 598, ECE 598, which talks about advanced wireless networks, advanced wireless sensing. 538 in the CS department talks about advanced networks like cloud computing, software-defined networks, edge computing, those kind of things. There are also theoretical cloud computing courses and theoretical networking courses that go into deep into the proofs and algorithms underlying these. And there are also IoT courses from the CS and EC department, which talks about various applications. You have to figure out where you want to be. This course was a little bit more algorithmic. There are also courses that are much more hands-on and experimental, and you have to figure out where you want to lie and take the course accordingly. There are several IoT courses that will be offered. My take is that programming you can pick up on your own, but some of these mathematical foundations are difficult to pick up as you go out and you go into the world. It will be difficult for you if you're working in Google or if you're working in Amazon 3 years, 4 years from now. It will be difficult to come back to the math and look at and figure out those math. So maybe it's worth taking some of the mathematical courses, especially in signals and systems and sensing, while you're still in the university. And of course, if you're going to go to grad school, then this mathematical algorithmic point of view is going to be very helpful. Okay, that's all I have for this class. I'm happy to answer any questions. Deep says on the chat, there's a new course being offered next semester, 498 ML in wireless networks. Oh, I didn't know about that. I don't know about that, but it's a 498, so it's a new course. So feel free to look at it. Any other questions? I certainly urge you to please fill in the ICES evaluation. If there are good things that you liked about this course, please let me know, because that way I know I should keep them. I should not remove them. And if there are things that you think were not good, you hated about this course, you want things to change, let me know. I will definitely make sure, I will make sure I take those feedback into account. Anything else we can talk about? Shreyas, you wanted to
I had something to share.
Yeah.
Yeah, I know we're over time already, but if you guys are interested in data visualization, this might be fun or helpful. I don't know how helpful it is, but it is certainly fun. Let me share my screen.
Sure.
Okay, so I hope you guys are familiar with the XKCD comic. If you're not, you should be. This is an example. It's like a very technical / nerdy comic. I'll give you a couple of seconds to read this. Mostly centered around like anything technical or even data related or anything going on in like science. Occasionally he also has comics about like scientific papers and graphs. So these are sometimes interesting to read. Maybe Professor will relate with this. Here was another example. So I recently realized, and I thought I'll share with you guys, that Matplotlib actually has a way to make charts more fun by making them XKCD style very easily. So these are, I just have some like a gallery of examples of figures of using Matplotlib. I hope you guys had a fun time playing around with that throughout this course. So this is how, like, you know, the graphs end up looking like. But what you can do is just add a line tlt.xkcd, and once you run that, any new plot that matplotlib plots will be converted into an XKCD style. So let me run this cell again, and it looks like a cartoonish sketch.
I see.
Yeah.
I see.
It actually has really good support. Let me run all the cells so you can see something like this. So I started to submit all my homework with this style because technically it is an accurate plot. I'm glad that I showed this to you last day of class so that you don't do that with us. Yeah.
Hey,
So have fun with this.
there's one MP still remaining, Shreyas.
Yeah, I know. Hopefully we won't have a bad time. Here's some more examples, like with more advanced plot. Like we have histograms here, just generic style. Let me
Show me what that histogram would look like with the XKCD.
Sure. I'm running all the cells again now with this line. Just remember this plt.xkcd. This is what it looks like now.
Cool.
Professor, maybe this is good for scientific papers as well.
Maybe.
Yeah. And it also works well. I have some more examples here for you. Some of these don't work, but yeah. It also works for 3D plots.
Perfect.
Here are some box plots with error bars and stuff. Oh, yeah.
Wonderful. That's terrific. Yeah. Thanks, Shreyas, for sharing
and
that.
Pie charts and stuff. It just works. So yeah, definitely give it a try. It also works with all different kinds of formatting, so you can still play around with colors. And heat maps is the last thing I have for you guys here.
Oh, nice.
Yeah.
Terrific. So thanks, guys. Any other questions that I can answer? None. We don't have a finals, so please focus on MP6. MP6 is dynamic time warping. Please also give feedback to the TAs. I hope, for me, it was a great experience working with these TAs, and I hope it was so for you too. I mean, there are glitches, of course, there are glitches that pop up every now and then, but if there's anything that you want to give feedback to about, please do. And TAs would appreciate if you really like the TAs, please recommend them for certain TA-related awards and TA-related honors. And if there's anything else that you want to talk to me about, email me anytime. I'm available. If it's about grad school, if it's about career looking forward, industry, jobs, preparing for interviews, I'm very, very happy to talk to you about this. Okay. With that, thank you very much. It was exciting to talk to you throughout this semester. I enjoyed teaching this course. I hope you learned a little bit, and I'll see you around. Stay in touch with Illinois, and I'll see you around. Okay, great. I'll hang back for a little bit if any of you have any questions, but other than that, thank you and have a great career.
Thank you, Professor. It was a fun class.
Thanks, Adil.
Thank you.
Thank you.
Thank you.
Thanks. Bless you.
I was going to say thank you. This has been one of the more interesting classes of my college career.
Thank you, Daniel. That means a lot. Thank you.
Have a nice day.
Sure, you too. You too. Yeah.
I do have a question from 2 lectures ago because I missed that lecture.
Can I ask you a question before you ask me a question?
Sure.
Are those paintings behind you watercolors?
They're my roommates, but I think I didn't draw them, obviously, but they're like calendar decorations.
Oh, that's wonderful. Let me stop recording if you have questions.